Okay, let's get back to Module 3, and the second part of Module 3 is on measures of variability. We're going to look at the range, the variance, and the standard deviation as measures of variability. Most of our efforts here will be focused on the variance and standard deviation. As we'll see, the range is a very simple measure of variability, but it doesn't have too much usefulness for our purposes. But let's start with the range. Most of you already know how to calculate a range. It's simply the difference between the largest number and the smallest number in the set of data. A couple of flaws to the range. By using only two numbers, it ignores variability between those two numbers. I could have two classes that on an exam had the exact same range of scores. Maybe the highest score was 90 and the lowest score was 60 for a range of 30 points. But that doesn't tell me that the variability between those numbers would be the same for the two classes. So by focusing on only two numbers, it has some severe limitations. We want to move on and talk about the variance and standard deviation. Now, a few of you in the class might be familiar with these already, depending on how much math you've had. But for a lot of you, you've perhaps never seen the variance and standard deviation formulas before. Like we did earlier with the mean, we're going to want to distinguish a population variance and standard deviation from a sample variance and standard deviation. Let's start with the variance. First, let's give a definition. Technically, the variance is the average squared deviation around the mean. That's kind of a mouthful, and I'll explain that a little bit more in a minute, step by step. Let's go to a formula first. For a population, the variance is going to be denoted by the symbol sigma squared. This is the lowercase Greek sigma, and we call this sigma squared. And again, as the formula shows you, you take the sum of xi minus mu quantity squared over n. In other words, we're going to calculate the mean first, take every value of x minus the mean, square those, add them up, and divide by n. Let's kind of explain the logic first to a variance, why we're doing this. First, as we've already talked about, we want to measure a variability that uses all the numbers, all the data, which the range did not do. So suppose we have a population of numbers, a population of values x1 through x capital N. Mu represents the mean of that data. The first thing with a variance we ask is if we want to measure variability, we could ask the question, variability relative to what? Well, the variance is going to measure variability relative to the mean value. We could take each value of x and see how far it deviates from the mean. In other words, by calculating the quantity xi minus mu. I sometimes call those the deviations around the mean, or sometimes I just call them the deviates. Every value in the data set deviates from the mean by some amount. Now we could just add those deviations up. We could sum the deviates. But that wouldn't do us any good. It would always give us a value of 0. And I ask you why. If you think about it for a moment, since you learned earlier that the mean was the balancing point of a distribution, some of these deviations are positive. If x1 is bigger than mu, then the deviation x1 minus mu is a positive number. But if x2 is smaller than mu, then the deviation x2 minus mu is a negative number. And remember, if the mean is really the balancing point, then the positive and negative deviations have to balance out. So the deviates will simply add up to nothing. Or as I like to remind my students, since deviates add up to nothing, you don't want to be a deviate in life, right? There's one of my few statistics jokes for the semester. Now, how could we prevent these deviations from adding up to 0? Well, we could do that by squaring them. Notice in the formula, that's exactly what we do in the numerator. We square the deviations around the mean. Remembering your math, something squared cannot be negative. And then lastly, we divide by n to basically average the squared deviations. That is, where else have you seen a sum divided by n? Well, the mean of the data is, of course, a sum of numbers divided by n. So that's why we say that the variance is really the average of the squared deviations around the mean. Now, one slight problem with the variance is that by squaring all the units of measurement, or by rather squaring all of those deviations, we've sort of squared the units of measurement in the problem. That is, if I have data on people's heights in inches, I now have squared inches. If I have wage rates in dollars, I now have squared dollars in a sense. One way to get around this is to take the square root of the variance. That is, after we calculate the variance, take its square root to, in a sense, get back into the original units of measurement. That square root is called the standard deviation of a data set. So if sigma squared is the variance and you take the positive square root of it, you will get sigma, and sigma is called the standard deviation of the population. By the way, don't confuse the variance and the standard deviation. If I ask you to find a variance, I'm asking you to find sigma squared if it's a population variance. If I ask you to find the population standard deviation, it's sigma. If you know one, of course, you know the other. If you know the variance, you can get the standard deviation by simply taking the square root of it. If you know the standard deviation, you can get the variance by squaring it. Later in the course, we're going to get to some formulas that require sigma and some that require sigma squared. So you want to keep the two separate and straight. I'm going to give you an alternative formula for calculating a population variance. On the left, we have the formula we've already looked at. If you wanted to use this formula, you first have to find the mean, mu. Then you have to calculate all the deviations around the mean. You have to square them, add them up, and divide by n. You can show with some mathematics that if you squared out this numerator and played around with it algebraically a little bit, you'd get the term on the right. Summation x squared minus n mu squared over n. In either formula, there's some work to do in the calculation, and it's not an easy thing to calculate. It will help to have a calculator do some of the work for you. One advantage of the formula on the right-hand side, if the mean is a fractional value, then sometimes calculating these deviations around the mean gets a little tedious. On the right-hand side, you only use the mean once. You square it here once. That also means that it actually has less rounding error. If you had a mean that is fractional and you round it, the formula on the right would give you less rounding error. However, other than that, if the mean's a whole number, the two should give you the exact same value. Let's do an example or sample calculation. Supposing I just gave you the numbers 47243, right here, 47243, and let's treat this as a population. If you want to use the first formula, you need to first calculate the mean, add those numbers up, they add up to 20. So the mean, the population mean is 20 over 5 or 4. Then again, using the first formula, let me go back to the formula. Using this first formula, after you have the mean, you have to find all the deviations from the mean, xi minus mu. So I've got a column here for x minus mu. 4 minus 4 is 0. 7 minus 4 is 3. 2 minus 4 is negative 2, etc. Notice, as we said before, those deviations around the mean add up to 0, so that's why we next have to square those deviations around the mean. 0 squared is 0, 3 squared is 9, negative 2 squared is 4, and so on. Those add up to 14. Lastly, once we have the sum of squared deviations in the numerator, we just divide by n to get the variance. So using the first formula, We will have a variance here of 14 divided by 5. 14 over 5 is 2.8, so that's our variance. Take the square root of that to get the standard deviation, and it turns out to be 1.67. Later on, we'll get to how can we interpret the variance and standard deviation and put a little bit more meaning to it. For right now, we're just learning how to calculate it. If you wanted to use the second formula, again, you can calculate the mean first, square it, multiply by n, and you'll have this part of the numerator. The only other thing you have to calculate is this term. You'll need to square all of the x's first and then add them up. And then again, we'll divide the result by n here. So to use the second formula, I've added in this last column over here, x squared. Take your x values and square each of them. 4 squared is 16, 7 squared is 49, and so on. Add those up, they add up to 94. Looking at our formula then, that's this term now is 94. N was 5. The mean, as you'll recall, was 4, and you're going to need to square that. 4 squared is 16, times 5 is 80. So using the second formula, again, you'll have 94 minus 80, that's the 5 times 4 squared. Divide all of that by n of 5, and again, you're going to get the same result as before, because the mean was a whole number, so you're not going to have any rounding error. 14 over 5, or 2.8, is our variance as before, and the standard deviation will still be the same as it was a minute ago. Standard deviation was 1.67. Be careful with the term in the numerator, summation x squared. That says square all of the x's first and then add them up. Many times people sum the x's and then square that result. That's not what this term means. Like most things in statistics, if you want to get good at the calculations, you have to practice them. So here I've got a practice problem for you. Suppose we treat a population here as the following values: 5, 8, 11, 5, 11, 12, 6, 3, 5. I'll let you fill in the table and figure out the results. Now I'm going to give you the answers here on the next slide. You should get a mean of 7, a population variance of 11, and a population standard deviation of 3.31. But if you do this problem and you don't get those answers, then you need to check your work carefully. And after checking your work, if you still can't get those answers, you need to email me and send me your work and I'll take a look at it. Okay, let's move to a sample variance. Most of the time, as we talked about back in Module 1, most of the time we don't have the entire population of data. Most of the time we only have a sample of data. We're going to do something similar, and yet it's going to be a little bit different. We still have a sample of numbers, x1 to x little n. We're still going to look at the deviations around the mean, but remember the mean now will be the sample mean x bar. So we'll still look at the deviations around the mean, and we'll still have to square them so that they don't add up to 0. So we'll sum the square deviations around the mean. Instead of dividing by little n, our sample size, however, we're going to divide by little n minus 1. And this will be called s squared rather than sigma squared. S squared stands for the sample variance. As before, if we take the positive square root of the variance, we will get the standard deviation. So s, the square root of s squared, is the sample standard deviation. Let me back up to here for just a moment. You might be asking, why do we divide by n minus 1 instead of just little n? Well, actually, we'll get to that in a future module, but I will give you an idea now. Remember, S squared is an example of a statistic. It's a characteristic of a sample. Sigma squared, the population variance, is a parameter. It's a characteristic of a population. One of the things that we do with statistics like S squared is we will use them to estimate and test hypotheses about elements of the population. S squared, for example, could be used as an estimator of sigma squared. It turns out that dividing by n minus 1 actually makes S squared a little bit better estimator than dividing by n would. And as I said, we'll actually talk about that a little bit more in a future chapter, future module. Like before, I'm going to give you an alternative formula. If you squared out the numerator and did some algebra to it, you'd get the formula on the right. Again, very similar to what we did with the population. Summation x squared minus n x bar squared over n minus 1. Again, it doesn't matter which formula you use. Just be careful in the calculations. The formula on the left, you need to calculate x bar first, and then all the deviations around the mean. Square them all, add them up, divide by n minus 1. The formula on the right, you need x bar, square it, multiply by n, and subtract all of that from this term, summation x squared, which remember is you'll have to square all of the x's first and then add them up, and then take the result and divide by n minus 1. Again, let's do a practice problem. Let's go back to, I think this was the first set of numbers we used earlier in the chapter as a sample, 3, 4, 5, 8, 10. So treat this as a sample of data. Those numbers sum to 30, so therefore our sample mean would be 30 divided by 5, or 6. Here's all the deviations around the mean. 3 minus 6 is negative 3, 4 minus 6 is negative 2, 5 minus 6 is negative 1, and so on. Then we have to square all those deviations. Again, I'm using the first formula initially. Square all those deviations and you will get 9, 4, 1, 4, and 16, which adds up to 34. So if you want to use the first formula over here, the numerator is 34, the denominator n minus 1 will be 4, sample size minus 1. There were 5 elements in our sample size, subtract 1, that's equal to 4. 34 over 4 is 8.5. It would be our sample variance. If 8.5 is our variance, the standard deviation is the square root of that, or 2.915. If you prefer to use the alternative formula here, you'll need to calculate summation x squared. So that's why I have this last column over here. Take all of the x's and square them. 3 squared is 9, 4 squared is 16, 5 squared is 25, etc. They add up to 214. That's this term right here, summation x squared. So we have 214 minus 5 times 6 squared, all over 4. Again, we're going to get the same answer as with the other formula, because the mean was a whole number and we didn't round it. 34 over 4, or 8.5. And again, the standard deviation will be the square root of that, or 2.915. Again, I encourage you to do some practice. If you've never calculated a variance or standard deviation before, you need to practice. And while I am going to show you how to do it on a TI 83 or 84, you should always know how to do it by hand, just in case your calculator malfunctions or your batteries burn out and you need to be able to do this. So here's a practice problem for you. Treat this as a sample, 4742963. Calculate the variance, actually I'll say the variance and standard deviation and mean of the sample. And I'm going to give you the answer on the next slide, or the answers. You should get a mean of 5, a variance of 6, and a standard deviation of 2.4494. If you don't get those and then you know you've made some errors, go back and check your work and try to figure out what you did wrong. And if you can't figure it out, send me an email. Okay, let's talk a little bit about how would you find some of these descriptive statistics that we've been calculating if you have a TI 83 or 84. First, when you enter data in a TI 83 or 84 or in just about any computer program, generally data goes in lists, straight up and down a vertical list. On your TI 83 or 84, you can access lists by pressing the Stat button first, and then hit the number 1. And it'll take you to a bunch of lists. You should have 6 lists on your TI 83 or 84. They're labeled L1, L2, L3, etc. Enter your data in one of the lists. So for example, let's go back. If you were putting this data in a list, you'll just put the numbers in a vertical list, 4, 7, 4, 2, straight up and down. So put the data in a list. Keep track of where you put it. After you've done that, press the Stat button. At the top, scroll over to the right to where it says Calc, C-A-L-C. And number 1 should be highlighted. 1 variable stats, it's abbreviated. Press Enter. And now the calculator is waiting for you to tell it where's the data that you want me to do these statistics on. If you put your data in L1, you'll hit the second level button and then the number 1 to access L1. And then hit Enter. The calculator should then give you the mean of the data. It'll label it as X bar. The calculator, by the way, doesn't know if you are treating the data as a population or a sample. So when it gets down to the standard deviation, it gives you 2 versions of it, the sample standard deviation and the population standard deviation. There'll be a number of other statistics. If you scroll down, it'll give you the median, tells you the minimum and maximum values from which you can get the range, and a number of other things. But for now, we're primarily interested in the mean, the standard deviation. You could then take the standard deviation and square it to get the variance, and so forth. There will be times when you have to clear out a list from old data. To clear a list, press your Stat button, and then notice number 4, alternative number 4, is clear list. So if you hit number 4, and then you have to put in the number of the list you want. So if you wanted to clear L1, you'll have to hit second level number 1 to get to L1, and then hit the Enter button. And the calculator will say done, and it's cleared the old data out of list 1. If you use a TI 83 or 84 on any homework assignments or things you have to turn in to me, I do require that you explain all of your steps. What did you have to plug into your calculator and where did you put your data, etc., in order to get these results. Okay, one last thing that we're going to cover in this section. Just a few notes on variances and standard deviations. First, you should be able to see immediately that a variance can never be a negative number. Why? Well, let's go back here to a formula. Here's the sample variance. Since a variance is a sum of squares, things squared can't be negative. If you ever get a negative number for a variance, you know you've made a mistake. And you could do that, especially with the formula on the right, the alternative formula. If you accidentally have summation x squared here smaller than nx bar squared, you'll have a negative in your numerator, but that's impossible. You calculated something wrong. So if you ever get a negative variance, this big gong should go off telling you you've done something wrong. Can the variance of any set of numbers ever be 0? There's only one way. If you think about it, it should make sense to you. The only way to ever get a variance of 0 is if all the numbers are exactly the same. In other words, there is no variability to the numbers. If I give you the numbers 5, 5, 5, 5, 5, 5, and say what's the variance, the answer is 0. They didn't vary. The mean of all those numbers would be 5, and all the deviations around the mean would be 0, and that's the only way you'll ever get a variance of 0. And the last thing that I'd like to point out here is even though you need the mean to calculate the variance is actually independent of the mean value itself. In other words, two distributions could have different means, but they could have the same variance. Quick little example I give you here at the bottom. Let's say variable x is the numbers 10, 20, and 30. The mean of those three numbers is right in the middle, 20. Just add those three up, divide by 3, you'll get 20. Y is 100, 110, 120. The mean of those three numbers is 110. So these two variables have different means. But if you look at it, you'll see that they have exactly the same variance, because the deviations around the mean would all be exactly the same. Variable x has one number, 10, which is 10 units below the mean of 20, one number right at the mean, and one number that's 10 units above. Same thing with y, one number 10 units below the mean, one number right at the mean, one number 10 units above. So if you calculated the variance, you'd get exactly the same number for x and y. Of course, you might notice that all I did to go from x to y is I took x and I added 90 to every number. 10 plus 90 is 100, 20 plus 90 is 110, etc. If you add or subtract a constant from every number in the data set, you haven't changed the variance. You've changed the mean, but you haven't changed the variance. Okay, that's the end of part 2, and we will be moving on to part 3 then.